Well, hello, everybody, and welcome. My name is Roger Siegel, and you are watching AP Physics C, Electricity and Magnetism on the AP YouTube channel. This is our third night, and we're coming to you live. I am talking to you from my living room in Sarasota, Florida, and my friend and co-teacher, Kristen.
Hi, I'm Kristen Gonzalez-Vega, and I teach at Reedy High School in Frisco, Texas.
Wonderful. So just welcome tonight. If this is your first night with us, welcome. We have all of our shows are recorded, so you can go back and look back and see. And so you should be able to follow, and everything we're doing is right from the AP curriculum, which is on the AP website. So we hope you can follow along with us. All right, so let me go ahead and open up our PowerPoint for tonight. And that will be here. All right, and so here we are, AP Physics C, E&M. And tonight we're going to talk about magnetic fields from current carrying wires, okay? We'll review for a second and we'll swing back to that. The first thing, I already told you my name, Roger Siegel, and coming to you from Sarasota, Florida, and Kristen is from Reedy High School in Frisco, Texas. All right. So the first thing we do want to let you know, and this could be your first night, is to know about the material we're covering. So today and for the next week, we're covering material that the colleges have asked all AP students to study, even if it's not going to be on the AP exam. So most of what we're doing tonight, 95% of it, you will not see on the AP exam tonight. But we have an agreement with the colleges. We want to cover this and treat it seriously. We think it's important. It's magnetism. It's what we're working on. So it's going to be what we're studying. And that way, when you do go on to college, when magnetism comes up, you won't be totally a neophyte. You'll have had some experience with it. So that's where we're going with this. All right. So first thing I want to do is review and talk about the first 2 days that we've been here. So Wednesday night, that was unit 4.1 Wednesday night, magnetic force on a moving charge. All right. And so for that one, you remember we had a moving charge, a charge moving through some kind of magnetic field. And the force on that charge is given by Q times V cross B, which gives us a cross product gives us the right-hand rule. And we found that when we have a charged particle moving through a magnetic field, there's 3 different possibilities of its path. It is either going to go in a straight line. It will not curve one way or another, and it'll go in a straight line at a constant speed. It can go in a helix, a spiral at a constant speed, or it could go in a circle at a constant speed. And since all of these motions and changes in motions, if you will, do not change the speed of the particle, the magnetic force does no work on the charged particle. Okay, and so that's what we did on Wednesday. And then on Thursday, we talked about the magnetic force on a current carrying wire. Now, a charged particle is different than a current carrying wire on some level. But if we were to drill down and be able to look at a wire with a current moving through it, we would see that there were moving charges. So these are very similar, these two ideas. And so here we have another right-hand rule. The magnetic force on a current carrying wire is the integral of I dot dl cross B. And again, a cross product gives us a right-hand rule. And often, and I'm going to say 85 to 95% of the time, often this formula simplifies to F is equal to BIL, and we will see that tonight. All right. Now, so what's new? That's what we've done. After today, what we're going to talk about today is, let me back up a minute. So day 1, magnetic force on a particle. Day 2, magnetic force on a current carrying wire. Day 3 is how do we generate a magnetic field? And so today and moving forward a little bit, it's about the magnetic field on a current carrying how a magnetic field gets generated. Now, what you're most familiar with a magnetic field getting generated is a permanent magnet. And so a permanent magnet has a magnetic field around it all the time. And it's a great way to store your pens. There we go. And that's a beautiful permanent magnetic field on it. All right. But what we study in this class is the magnetic field that comes from a current carrying wire. All right, so first we have, we're going to calculate that magnetic field. We're going to have a new right-hand rule, a third right-hand rule, if you will, for telling us the magnetic field's direction. We're going to describe the direction of the magnetic field vectors at points near this wire, okay? And we are going to calculate the magnitude of the magnetic field at various points near the wire, calculate an unknown current, and that's one of the problems that we'll do today. And then the force of attraction or repulsion between two long, straight current-carrying wires. And finally, describe the consequence of attract or repel when two long, straight wires, long, straight current-carrying wires have known current directions. It's a lot to talk about, but it actually is, it looks like more on this page than it really is. I think you'll be able to follow along just fine. All right, so first of all, let's review. The previous 2 days, we looked at two different right-hand rules. First, we had the right-hand rule on Wednesday, and this is the right-hand rule for the forces on a charged particle moving through a magnetic field. And remember, this was our Q times V cross B. Okay, sorry about that. Okay, there we go. And over here, this is what we did on Thursday, and this is our current carrying wire and the force on it. And I want you to notice how similar these two are. Extremely similar. And that should make sense to you, because if we have a charge that's moving, that's going to be coulombs per second moving, okay? If we have a current, well, you know, the unit for current is also coulombs per second. So these are very, very similar. And so hopefully it makes sense to you like that. All right. Now we've got a new situation. Instead of asking what's the force on a particle, what's the force on a wire, we're going to ask what is the direction of a magnetic field created by a current carrying wire. So this is our picture for that, and you can see that what we have is this particular right-hand rule. And so let me go ahead and switch over to my document camera, and I want to show you, I've got this printed out, but I just want to be able to do this. And so we imagine that we've got a current, a wire has a current going through it, all right? And what you learned in probably your 7th grade physical science class, what we learn in this class is that when we have a current going through that wire, that creates a magnet. It's called electromagnetism. And an electromagnet is just a magnet caused by a moving current. And we want to know how much magnetic field is created, and we also want to know what's the direction. Now, first, let's do the direction. Third right-hand rule. We take our current carrying wire and we act like we're with our right hand, we're going to grab the wire, okay, with our thumb in the direction of the current. Now, what that means is when the wire is coming at me, that current is going, that magnetic field is going to have a counterclockwise direction. And if that current is facing away from me, then that magnetic field will have a clockwise direction. All right. Now, we've got some good visualizations to help you see this. We're not going to just ask you to look, try and imagine everything we're talking about. We've got some good simulations. So let's go ahead and take a look. Let's go back to the PowerPoint at the next slide. Now, the right-hand rule tells us the direction of the current carrying wire, but this formula tells us the magnitude, okay? And so you can see this formula is the magnetic field B is equal to mu naught I over 2 pi r. Okay, now that is a formula that you will not be tested on. And for some reason, that formula is not on the AP Physics C formula sheet, even though it's probably the most used formula in magnetism. But there are reasons for that, and so we'll move on. But I did want to talk about this for a minute. Let's make sure you understand everything that we have here, everything that this is. So I'll bet I'm going to just kind of go back here, and I'll bet that everybody knows what, of course, 2 pi is easy. R is the radius or the distance from the center of the wire. Okay, and so you probably would have imagined that as well. Okay, I, of course, is the current. And now we have something that I don't think you've ever seen before. I think this is the first time we've seen this quantity. And this is a fundamental constant of the universe. As much as capital G is a fundamental constant of the universe, or as much as epsilon naught is a fundamental constant, the vacuum permittivity that you learned about earlier when you learned about electric fields. Now we have magnetic fields, and we have the permeability of free space, or the magnetic permeability of a substance. All right, so I have a slide for that because I think it's important. What is mu naught? So mu naught is the measurement of the resistance, or permeability is the measurement of the resistance of a material against the formation of a magnetic field. Okay, so some materials are just happy to have a magnetic field flow through them, and some materials are like, whoa, not so much magnetic field. And that's how we measure that with the permeability. Okay, now mu naught is the permeability of free space. Okay, and so this is the number that we're going to use, and this is on a formula sheet. So if we were doing problems with this is how we would find mu naught. It would be 4 pi times 10 to the minus 7, and the units are newtons per ampere squared. All right. I would not lose any sleep over trying to understand mu naught. It's not really something we have to understand at this level. However, I would be remiss as a physics teacher if I didn't tell you something very interesting, because I know all of your physics teachers would want me to tell you this, and that is this. When Maxwell derived his equations, Maxwell's equations, he found that these two constants, 1 over epsilon naught times mu naught, which, remember what those are, that's the vacuum permittivity of free space. That's how much free space resists an electric field. That's the vacuum permeability of free space. That's how much free space resists a magnetic field. That is equal to none other than the speed of light. And so that is a beautiful piece of how amazing our universe is. And if you go forward in E&M, you will see that show up again. It is an amazing idea. All right, let's go back and talk about what we have next. So we said that visualizing the magnetic field says we're going to draw a vector representing the magnetic field at the points marked. So let's look at these points. I'm going to scooch over here a bit, see what we have. And so this means that my current is going into the board. And so I'm going to put my hand and my thumb in that direction. And notice that my fingers curl, and I'm going to go ahead and use a light color here. My fingers curl in this direction. All right, now draw a few concentric circles here. And so what we imagine is that the magnetic field everywhere concentric to this is, again, notice I hold my hand, fingers curl in a clockwise direction. So the magnetic field at this point is this much. I want to write the formula again. B is equal to mu naught I over 2 pi r. Okay. Now, what does this R mean in the denominator? Well, it means the further we go away, the more or the less our magnetic field is. So that means if I'm closer, I'm going to have a greater magnetic field. And this one, I believe, is even closer. So it'll be even longer. And this one is even closer. And so it'll be even longer. So the magnitude of the magnetic field is greater the closer I am to the current carrying wire, and it falls off as I move away. The direction is given by, since the current is into the board, my thumb goes into the board, and my fingers curl in the in the clockwise direction, like this. The next one that we have is the magnetic field, but look at what's different here. Now we've got a dot, and that dot means that that field is coming out of the board. So let's see, I'm going to start with a little, the one that's closest here, a little pencil, and I'm going to draw a concentric circle around there. Okay, let me draw another concentric circle around this one. I think this guy holds both of these, and let me throw it around this one. Okay, all right, and so I'm going to use the right-hand rule. My thumb points out at the paper because that's the direction of the current. And so that means that all of these magnetic fields are pointing in the counterclockwise direction. This one is the closest, so it's going to be the longest vector. These two are a little bit further away, so they will be smaller. Again, counterclockwise. And this one's the furthest, it will be the smallest. And again, remember, we're using the formula. B is equal to mu naught I over 2 pi r. And so that tells us how much, not only the magnitude of the field, but also its direction. Okay, so there's one more thing I want to show you before we start doing a few more problems, and that is the Falstad 3D magnetic field circuit simulator. Now, Mr. Falstad, I've never met him, but makes some of the most amazing physics and math simulations that you'll ever see. And I never go a year without teaching without using Mr. Falstad simulators. So as soon as we get these PowerPoints into the comments section, you can click on this. I'm going to take you there now. And this is, again, a website, so this doesn't cost us any money. And this is a magnetostatics application. Now, what we have here, I'm going to just have to move something around on my screen so I can see it. So what we have here is a simulation of a wire. Okay, now you can look, let's see if I can aim this wire so it's facing just straight right at us. It's not as easy, it doesn't respond as quickly. Let's try this very slowly. There we go. Okay, now you can see this wire right here, and around this wire, these circles represent the magnetic field created by the wire. And this white circle means that we've got a higher or stronger magnetic field, and then the green circle means it's weaker, and the further we go out, the weaker it is. But you want to imagine these concentric cylinders surrounding the field, the wire, and that's what its field is. Okay. So we are going to send it over to Frisco, and Kristen has some great problems for us to work on next.
All right, thanks, Roger. That simulation is pretty neat to see. We're going to look here now at what happens if we have more than one wire or more than one magnetic field that is occupying a region of space. So if we have here 4 wires, 1, 2, 3 of them are coming out, the current is coming out of the page, and the 4th one, the current is going into the page. So we want to look at what happens if we have multiple magnetic fields. So we're just going to draw some lines here. And if you don't already, it is a good idea to get out some paper and be doing these with us. So I'm going to label them as different colors so that we can tell them apart. So if I look at the first one at the top here, the current is coming out at us, right? So it's almost summertime. So I use today to get out my pool noodles. So this is my wire, right? So if this is our wire, the current is coming out towards you, we can do this grip rule, right? Current is coming out, we're going to grip that wire around. So if the current's coming out, it's going to go around counterclockwise around that wire. So I'm going to draw including P. So I could draw, we'll draw a few of them just to get in. But really what I care about is going through that point P, which way is the magnetic field? So again, if it was coming out and it's going counterclockwise at point P, it is tangent to that circle at any point, so it would be to the right. Okay, so we're going to do the same thing for all three of them. You do them, see if you can get ahead of me while I'm doing it, and we want to find out what would we do with those magnetic fields at point P. So I'm going to label this one number 2. And since this time our current is going into the page, fingers are pointing inside here, and now my fingers grip around and curl around clockwise. So now we're going to draw those around clockwise, and that means at point P, that magnetic field is going down. Okay, so if we look at wire number 3 here, again, this one's going out of the page. So thumb is coming out towards me, again, counterclockwise. Which means at point P, that magnetic field is going to the left. And then lastly, let's do some sparkles. We have again, the current is coming out towards us. So again, it is going around counterclockwise. So if we go around and include in point P, we also have the magnetic field going down at that point. So if I just kind of redraw these off to the side here, we had at point P, one magnetic field going to the right, we had one magnetic field going to the left, and we had two magnetic fields both pointing straight down. So if the current in here is identical, right, we know the magnetic field is equal to that mu naught I over 2 pi r. So if we look at the magnitude of these two, if the current is identical in those wires, then the current is going to be the same. We know that these are all constants, those are all the same. And if we look at the distance between each wire and point P, what's true about that? Well, it's also the same. So if all of these things are the same, then the magnitude of these two magnetic fields is going to be the same. One is to the right, one is to the left. What happens? They cancel out. So what we're left with is those two magnetic fields pointing downwards. So we get one large magnetic field pointing down. Okay. Now let's look at if we have two wires that are crossed here and look at point P. So point P is at a distance of r from this wire and at a distance of 2r from the other wire. And we have the current directions there. So the first thing I'm going to do is look at each one and draw the magnetic field due to each of those wires. So if we look at the first wire, and we've got that current that is going down to the right. So now I'm going to point my fingers down to the right. And as I grip around, well, on the one side that's coming out of the page, and on the other side, it's going to be going down into the page. So we're going to be coming out of the page everywhere over here. And that's everywhere. It could go on and on and on. So I'm going to draw lots of dots coming out of the page for that magnetic field. And if we do the same thing with the blue wire, well, the blue wire has a current going up to the right. So again, if we point our fingers up to the right, we grip around, we're going out of the page, into the page. So we've got, again, out of the page and all of this region here and into the page in this region here. So let's look at point P. And then I kind of want to talk about these other parts too. So let me fill in also. We did the out of the page. We didn't do the end of the page here. Okay, so if we look at point P, let's take each field on its own independently, right? So if we look at the kind of fuchsia wire here, then it would have a magnitude B, since the equation is 2 mu naught I over 2 pi r. Then what is our values there? Well, the I is I, the R is R, so we're good there. Let's look at the blue wire. The blue wire is the same equation, same current, but the distance away from point P to the center of the wire is 2r. Okay, so if we look at the magnitude of each of those two, now we want to look and see, just like we did with fields or any other vector, we want to look and see the direction of those. So if I look at point P, they're both coming out of the page. So if we have two vectors that are in the same direction, what do we do with them? We add them together. Okay, well, we want to get a common denominator here, so 2 over 2, and we end up with 3/4 times mu naught I over pi times r. And that would be for point P. So let's look at these other regions here. If we look at, let's call this region 1. If we look at region 2, then what would happen? Well, there, since you've got one of those magnetic fields coming out of the page and one of them going in, we'd subtract them. Okay, again, in region 3, both going in the same direction, we add them. And in region 4, opposite direction, so we would subtract those again. So even though you're looking for the field at one point, it's always still a good idea to draw a large region of the field so you can kind of get a big picture of what's happening. And where that's kind of most important is when we have two wires and we're going to talk about the force. So that's the field. And why is that field important? Well, if I have a wire that has a current going through it that's in a magnetic field, what does it experience? It experiences a magnetic force. So if we look at these two wires, they're going to have a force on each other. And it turns out, and I'll show you here why in a second, if your currents are traveling in the same direction, those two wires attract each other. And if your currents are going in opposite directions, they're going to repel each other apart. And so if we look at one of these examples, let's look at these two wires where the current is going into the page in both of them. So do your grip rule and draw me, so I always kind of like to use one of my wires as like a reference wire and then see what happens to the other one because of that. So let's call this guy our reference wire. And so I want you to draw me some field lines, magnetic field lines going around that wire. And then we'll talk about what's going to happen then to the effect wire, right? Or the second wire. So I'll give you just a second to draw those. So if we look at that wire and the current is going into the page, right? So if current's into the page, we grip around, it's going around in that clockwise direction. So we've got, I'll just draw a couple of them. Really what I care about is what's happening where that other wire is. So if I look at that other wire, and let's put some directions on here, at this exact point in the center of that second wire, which way is that magnetic field directed? It's directed downwards. Okay, so now I'm going to ignore the other wire. It's almost like it doesn't even exist anymore. If I now look at just the wire on the right that also has a current going in, let's bring back our right-hand rule and look at what would happen to the force on that wire. Which direction would the force be on this wire on the right? Well, if the current is going into the page, remember we've got our 3 fingers now, right-hand rule. Our finger's going to point in the direction of the current. Our middle finger is the field and our thumb is the force. So if this wire has a current that's going into the page, then my first finger's pointing into the page. My magnetic field is down. Well, look which way my thumb is pointing. My thumb is pointing to the left. So it's going to have a magnetic force to the left. And what's that going to do? It's going to draw it in towards the other wire. And we could do the same thing on the other one too. If I look at the magnetic field due to now my effect wire, it's also into the page. So it has a magnetic field going around it as well. So again, into the page, clockwise. So if we look at just this one that's going to go through here, it has a magnetic field going up. Okay, so if that magnetic field is going up, B field going up. So if that magnetic field is going up, then we can do the right-hand rule again to determine which way that force is on it. So if we go current going into the page, and now our magnetic field is pointed upwards, now which way is my thumb pointing? It's pointing to the right. So it would have a force directed to the left. And if these are equal currents, right? If we know that force is I times L times B, and we know that the B is mu naught I over 2 pi R, well, if they're equal distance apart and the current is the same through them, then we could say that they're equal amounts of forces acting on each other. Okay, so let's look at then real quick at if they're opposite and what we would do for that. If I have the one on the left and it has a current going into the page, again, which way is the magnetic field going to be? It's going to be going around clockwise. So at this point here, we'd have that magnetic field going downwards. Okay, so let's look at how that's going to affect the wire on the right. Well, the wire on the right is in a magnetic field, so it's going to experience a magnetic force. So if the current is coming now out of the page, current's coming out of the page this time, my thumb's going to point out, I'm gripping around. Oops, sorry, we use our right hand rule. So if the current's coming out at you and the magnetic field is down, so current's coming out, I got to kind of put my finger out and the magnetic field is down. Well, now that force is to the right. And so those are going to repel each other. The next thing we're going to look at here then is if we have a current carrying wire and we have our electron. So let's bring our moving charge back into it from the other night. So if the current is to the left in here and we want to find what the magnetic force on the electron is. So I'm going to give you just a couple of minutes. Let's see if you can do this one. So you're going to draw the magnetic field around that current carrying wire. And then I want you to use your right hand rule. What would the force be on the electron using your right hand rule? I'm going to tell you to be careful on this one. Okay, so let's look at the wire and let's use our grip rule to determine the direction of the magnetic field. So if the current is traveling to the right, my thumb goes to the right, we grip around on the top of that wire, that magnetic field is going to be going into the page. If I keep curling, my fingers are going to come out on the bottom. So we got magnetic field in everywhere here, and we've got magnetic field out everywhere here. Okay, so this charge is now moving in this magnetic field. What did we say the other day you have to be really careful about? When you're reading the question, the first thing you check is what? What charge is your particle? And this is not a positive charge, this is a negative charge. So again, whether you're using the right hand rule and flipping it or using the left hand rule, I use my left hand, but so if this is an electron, we got to use our left hand or use your right and flip the sign. So the velocity of this is to the right. If our magnetic field is then coming out at you, which way is your force? It is up. Kind of like my voice just went. So that experiences that upward force due to that magnetic field. Okay, so we get lots of interactions here, which is really fun. Okay, I'm going to do one more, and then we're going to throw it back for an AP style problem from Roger. So what if we have a square loop instead of that electron? And let's find what would the force, the magnetic force, be on that square loop of wire. So again, I'm going to give you just a second to think about this one. Draw me some magnetic field vectors above and below that wire. And what do you think is going to happen in that loop? And if you need more time, you can always pause, come back. So right hand rule, again, this time currents to the right, into the page, out of the page. Everywhere in this whole region, into the page, out of the page. So if we've got that now magnetic field on the top here that's into the page, every part of that loop is in that magnetic field. Let's look at, though, how each side of the wire is affected. So we looked at some loops of wire yesterday and how that's affected by the magnetic field. So some of it we'll kind of go through fast and some of it we'll talk a little bit more about. I first want to look at those two outside parts of the wire. If those two outside parts of the wire have currents that are equal in magnitude, right? The current's the same everywhere in that loop. If the current's the same and everywhere in that loop, and those lengths of the wires are the same, and we know that the force is ILB, and every part of these equal sides are in the same part of the field, what's going to happen to the force on each of these sides? Well, if we still do our right-hand rule and we have our current going up and our magnetic field going in, we've got a force to the left on this side and to the right on this side. And those are going to cancel out. But what's not going to cancel out is the top and bottom. We can still do the right-hand rule and look at the force in which direction it is. On the bottom, if we have the current going to the left and the field is into the page, we've got a downward force. And since the current's on the opposite direction on the top, that's an upward force. But why do these not cancel out? Is the magnitude of the magnetic field the same on at both the point on the top and on the bottom? No, because the magnitude of the field is mu naught I over 2 pi r. Well, maybe the same current, but what is not the same? The distance away from that wire that's causing that magnetic field. So at here on the top, that magnetic field is a greater distance away. It's got an R, let's just call that of R1. Whereas the bottom has an R of R2. And that's a much smaller R on the bottom. So if we decrease this bottom part, we have a greater magnitude of the field on the bottom part of the wire, therefore a greater part of the magnitude of the force. So the net force on this is going to be the same direction that the bottom part of the wire experiences, which is down. Okay, hopefully that helped a little bit there doing those examples. Now let's get into one that we may see later on, not necessarily on this year's AP test, but what we may normally see on the AP test. So I'm going to throw it back over to Roger to finish up today.
Okay, thanks so much, Kristen. Great job. So the last thing we want to look at comes from an old AP free response question. And as Kristen said, won't be on this year's exam, but there is a little bit in here that you can enjoy and look at. A little bit of last year's exam, a little bit of this year's. We'll see. So I'm going to switch over to the doc cam. But if you do get a chance to download the PowerPoint, we're going right to this problem now. Okay, so it says this is from, first of all, this is from the 2001. Let's see. Did I share my screen? I don't think I did. Let me go ahead and do that. Sorry. All right, there we go. All right, so now we're looking at the 2001 exam. And it says the circuit shown above consists, or it's to the right, of a battery of EMF E in series with a rod of length L, mass M, and resistance R. The rod is suspended by vertical connecting wires of length D, and the horizontal wires that connect to the battery are fixed. All these wires have negligible mass and resistance. The rod is a distance R above a conducting cable. The cable is very long and is located directly below and parallel to the rod. Earth's gravitational pull is toward the bottom of the page. Express all algebraic answers in terms of the given quantities and fundamental constants. All right. So first of all, I do want to remind you that the 2001 exam is a public exam that's available on the AP website. So if you wanted to look at this and delve into it a little bit more, that's certainly something you could do. But I'm going to switch over to the doc cam so I can work through this a little bit. And so the first question says, what is the magnitude and direction of the current in the rod? And so let's look. I'm going to zoom in here. And what we can see is that the rod is right here. And so if we want the magnitude and direction of the current in the rod, remember I told you that this is a problem that could be on this year's exam? Here it is. So this is actually, if we want to know the magnitude and direction of a current in a circuit, well, I think you know where that comes from. That's Ohm's law. And Ohm's law says that the current is equal to V over R, or in this case, we don't have V, we have the electromotive force E, script E over R. Be careful, the capital R is different than the small r as this distance, okay? And so that would be the first answer. That's the magnitude of the current. The question is, what's the direction? Well, hopefully you remembered from unit 3 when we studied circuits that for conventional current, the current leaves the battery from the positive end and moves toward the negative. So that would mean that the direction of the current in the rod is going to be right to left. So that is the magnitude and direction of the current in the rod. Now, in which direction must there be a current in the cable to exert an upward force on the rod? Now, Kristen just showed us, and I'll remind you, that when we have two parallel wires that are current carrying wires that are parallel, that they attract each other. These two wires are parallel and they attract each other. But we want the cable to have an upward force, which would be a repulsion. And so that means that we need two wires that are in opposite directions or where the currents are anti-parallel. And so that's when we get repulsion, is when we have anti-parallel, so these are both parallel, these are attraction, this one's anti-parallel, and we have repulsion. So here we're going to say that the second answer, in which direction must there be a current in the cable, we're going to say the opposite direction, or left to right. Okay, all right. One more part to this problem and we'll be home free. Okay, so the last part says, with the proper current in the cable, the rod can be lifted up so that there is no tension in the connecting wires. So no tension in these wires here, right here, D. In other words, if there's no tension in these wires, that would mean that the force magnetic, this magnetic repulsive force, has to be equal to the other force pulling the rod down, and that, of course, is the force of gravity. And so I'm going to do some algebra and set these equal to each other. Force of gravity equals force magnetic. Okay. Now, the force of gravity does take us back to an earlier time, but that's always going to be mg. Okay. And the force magnetic, let's work through this. What is the magnetic force of repulsion between these? Well, yesterday we learned that when a current carrying wire is moving through a magnetic field, the force on it can be BIL. So this is going to be the magnetic field created by this wire, by the cable, and it's going to create a magnetic field right here, and that field, let's see, is going to be out of the paper. Here's this magnetic field that gets created. Okay, and what is the quantity of that magnetic field? Well, that magnetic field we've just learned today is mu naught I over 2 pi, and here's where my little r comes in, the distance from this wire, the magnetic field that is created by this bottom wire at the distance r of the top wire, 2 pi r. All right, and so that is going to be times I times L. Now, be careful. These two I's are not necessarily the same. This I is going to be the I in the cable. This I is the I in the rod, IR. But we know from the earlier problem that IR, that the I in the rod is equal to script E over R, over the resistance. So that's mu naught I C times E over R times L, and this mu naught IC has a 2 pi R in the bottom. So we're almost there. One last thing to do is what we want to do is, in this problem, solve for IC. That's what we're looking for. So I'm going to finish up my algebra. IC is equal to, and so you can see what's in the denominator over here is the 2 pi R and the R, and then we're going to have the mg. This is mg, 2 pi little r, big R, and then what's left is going to be here in the bottom, u naught E L, sigma script E L. And so that's our solution. If we have this much current in the cable, it's going to push up on this rod and there will be no tension in these wires. So that is the end of our lesson for tonight. I did want to remind you that we now have 3 right-hand rules. We've got the right-hand rule for a particle, we've got the right-hand rule for a current-carrying wire, and now we also have the right-hand rule for the magnetic field from a current-carrying wire. Okay. All right. So we hope that, again, you're enjoying these videos and that you can visit the AP Physics C Electricity and Magnetism website for more information. And so, Kristen, you want to give us anything?
I just hope you guys have a nice, restful weekend. Enjoy your family and tune back in on Monday.
Excellent. And I will say the same thing. I hope you guys have a wonderful weekend, and I hope everyone is healthy and well out there. And we can't wait to have you back here on Monday for more AP Physics C. Have a great night.